Welcome to part 3 in our series of videos on chemical equilibrium. Let's continue with our videos and see how we can answer more questions on NSC exam questions that can be asked based on chemical equilibrium. Okay, our question 3, which follow on the previous two videos, and I will encourage you to watch those two videos to get the foundation and to get introduction in some of the basic questions that can be asked. Doing those particular questions will give us a foundation to answer the following question. So we continue with question 3, and in this question we have a graph question, and hopefully one should find that the graph questions is a little bit easier once you know the foundations in terms of your theory and terms. Anyway, let's continue with this question. Question 3 comes from the November 2023 question paper, and it reads as follows. Consider the following hypothetical reaction reaching equilibrium in a 4 cubic decimeter closed container at 150 degrees Celsius. Now it's important to keep track of the temperature and the volume because we might use that in later questions. If you focus on the graph, you can see that this particular graph that we have here, we have the number of moles, and that will be on my y-axis, and on my x-axis we'll find the time measured in seconds. The graph shows the changes in the amounts of reactants and products over time. Now, in this particular reaction, the reactant is AB, it's a gas, and it decomposes into gas A squared and B squared. Both of these are gases. Now you can see that the number of moles of the reactants is 2 moles, and the total number of moles of my products will be also 2 moles, 1 mole each. They don't tell us anything about the temperature, whether it's an endothermic or exothermic reaction, so we'll find out that information if it's required later in the question. Let's go to the first question that they ask us, 3.1. Write down the meaning of the term reversible reaction. Now, this question has been asked before, so one can see that it's important, and do take note that you make an effort to remember that particular definition or how to describe what a reversible reaction is. Very short and sweet, this answer is the reaction where products can be converted back to reactants. So we're actually referring to back to the original reactants. 3.2, state the Lissatili's principle. Not the first time we've seen this one, and it reads as follows. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel, or you could say oppose, the disturbance. Now, it's very important. I didn't highlight it here, I should have, but it's very important to state that it is in a closed system. Remember in the theory we mentioned that a chemical equilibrium reaction can only exist or come into existence once you have a closed system. So that's important. Okay, our next question, in this case, a change was made to the equilibrium mixture at time t 80 seconds. So we can see there is time t 80 seconds, and we need to be able to write down what change was made at time t seconds. Now, in the previous question, we noticed that there was a sharp drop in the graph, and that was one of the lines was longer and the other one was slightly shorter. And when you get two lines that drop either down or go up, we know that is a change in temperature. If it was an increase in temperature, then those two lines would have gone upwards. In this particular case, we only see one line going up. Now, when you notice that one of these graphs it's only one sharp line going up or one sharp line going down, then we know generally it is concentration. If you find that in this case we have 3 graphs, you can see here's another graph on top of the solid line. If we had a situation where all three lines were either sharp up or sharp down, then that would have indicated a change in the pressure, or which will indicate obviously a change in the concentration of all the substances. In this case, that's not what has happened. It's only one of the reactants that has changed, so that could have been one of the factors that only influence one particular component. And because I can see that the graph over here on the y-axis indicates a number of moles, so it's a sharp increase of the number of moles of only reactant A. So that indicates to me if the volume stays the same and only the moles has changed, according to our formula C equals N divided by V, then the concentration is the factor that was changed in this particular case. Okay, so let's see what they say. So the answer here is the amount, we're referring to the number of moles, or the concentration of A2 was increased. Now, very important here, they want to know, write down the change made. So don't say that the change was only in A. Be specific in what type of change. And we can see from the graph, it was an increase and not a decrease. So say that an increase in the concentration of A2, what is what happened. The amount of A2 has increased. Or you can say that A2 was added to the container. Okay, added. So that's important because that tells us that it has increased. Okay, the second question, 3.32. Use Le Chatelier's principle to explain how the system reacts to this particular change. Now, in our equation here, we can see our equation, and I've highlighted it here again, just so that we can use it. I have AB decomposed into A squared plus B squared. Okay, so to answer 3.32, I can say the following. The reaction that uses or decreases the amount of concentration of A2 is favored. Now remember what we said in our first video. If a reactant is added, what the system is going to do, the system is going to do the opposite. So if it was added, the system is going to try to decrease it. And in trying to decrease it, it will either use it up or it will decrease the amount of A2 by converting it into something else. So in this case, we said uses or decreases the amount or the concentration of A2 is favored. And then the last point, because A is part of the products, we now know that to use A, we want A to react with B, and in doing so, I must favor the reverse reaction. So the last point we're going to say, the reverse reaction is favored. Okay, so that's important. Or you can say that A, the reaction of A with B will be increased to produce the original reactant. Okay, but it's much easier to say that the reverse reaction is favored. Okay, that's the answer for 3.32. Let's look at the following question. The next sub question is 3.4, and here they want us to calculate the equilibrium constant Kc at 120 seconds. Now, once again, I've put in the equation here to help us because we have to refer back to the equation. Now, at 120 seconds, I have the number of moles of compound B. I have the B squared. I have the number of moles of compound A squared. And I've got the number of moles of AB. Now, I can read that from the table, and I can use that in my calculation for Kc. Also remember that the volume here will be 4 cubic decimeters, and I need to use that. Okay, so there are two options that we can follow to answer this question. I've decided to focus on those two because I think they are the easiest to follow. There are other options, and I haven't considered that, but you're more than welcome to go and look at them. As I indicated, the question papers from November 2023. Okay, now having said what the different types of compounds are and the number of moles for each one, we have to remember that Kc equals A squared, that's B times B squared divided by AB. Now do take note in the equation that the mole ratio in front of AB, that will be the exponent I have to use here, and make sure that you use square brackets and not round brackets. Once you've written your formula down, you can use round brackets. Okay, now because I've indicated the number of moles and the volume that this reaction takes place is 4, for A, I'm going to use the flat part because that's the equilibrium part. Okay, and for A, I'm going to read that is 8 moles, so that will be 8 divided by 4, and then for B squared, it will be 2 divided by 4, and then for AB, it will be 10 divided by 4. Once you do that calculation, you'll see your answer is 0.16. Make sure that you take note that in this particular case, remember that Kc is only a value. It's a ratio between concentrations, so we don't have any units. The units for the denominator and the units for the numerator are both moles per cubic decimeter, and that will cancel out. And therefore, we have no units for Kc. Okay, that's the first option. The second option that we can follow to calculate this particular answer is fairly simple. And if I can get this one to move to the next one. Okay, I've got it. Let's see how we calculate this one. The formula will stay the same. In this case, you can do the calculation before the time. Here, what we've done was we've substituted the moles divided by the volume. Over here, you can first do that calculation. For 8 divided by 4 gives you 2, and then you substitute it in your formula. So this is concentration as I substituted, but in the previous calculation, I've used the moles divided by volume. So here's just 2 times 0.5 divided by 2.5 squared, and then that gives me the same answer, 0.16. It's important that you, for this calculation, make sure that you don't write an expression for Kc where you would say concentration of the products divided by concentration of the reactants. The examiner will mark that wrong. Observe your equation and use the symbols for the chemicals in your equation as your first step when you write down the equation for Kc. And make sure that you use square brackets, and then once you've used that in your formula, you can then, in your second step, when you substitute the variables or the values for the variables, you can then use round brackets and then calculate your answer. Okay, that's the answer for 3.4. Let's continue. 3.5, at time t equals 130 seconds, the temperature of the system is decreased to 100 degrees Celsius. Now, go back to the first part of your equation or your question or the information that they give you, and then have a look at what they've given you. Now, they've given us the original temperature as 150 degrees Celsius. Here, they say that temperatures decrease. Now, remember that temperature is the only factor that's going to influence Kc. So we can expect that Kc is going to change here to some degree. 3.5.1, draw a potential energy graph or diagram for this reaction. Now, if I look at my equation here, and I can see that this reaction has decreased, you would like to know, is the forward reaction endothermic or exothermic? You don't know that. They don't tell you anything. But you can go to the graph and you can see here, they tell us that t equals 130 seconds. So you go to 130 seconds and you can see just after 120 seconds, that's the part over here. Now at this particular part, you can see there's an increase in the moles of AB. There's a decrease in A squared, and there's a decrease in B squared. Now that tells me that the reactants constant number of moles have decreased, which is the same. I can say that the concentration of of concentration of product A and the concentration of product B has decreased, and the concentration of reactant AB has increased. So that tells me that the reverse reaction was favored by a decrease in temperature. So the reverse reaction must be exothermic. And then the forward reaction will be the opposite, will be endothermic. Okay, so when you're going to draw a potential energy diagram for this reaction, you're actually going to draw it for the forward reaction and not the reverse reaction, unless they ask you specifically for the reverse reaction. But if they just ask you to draw a potential energy diagram for this reaction, they are referring to the forward reaction. And we know that the forward reaction, as we worked it out from the data from my graph, is going to be endothermic. So that is going to be the graph that I'm going to draw. In endothermic, this indicates the energy for the reactants, and that indicates the energy for the products. And this must be higher than that part. And you're going to get 3 marks for that. Okay, but it takes a while to get to the answer. Okay, so as I explained that, go to the time that they've given you, and then see what has happened to the number of moles. And whatever you notice with the number of moles that has happened, the same is happening with the concentration. Okay, so the next part of this question is 3.5.2. Will the equilibrium constant Kc at 100 degrees Celsius be greater than, less than, or equal to the Kc at 150 degrees Celsius? Explain your answer. And in this case, it will be less than. And our reasons or explanation, the amount or the concentration of the products decreased. Okay, as I explained, the concentration of B squared and the concentration of A squared decreased, and the products have, and the reactants have increased. So if the reactants increase, if my denominator increase, then Kc will decrease. And if my, or you could say that my products have decreased, and then therefore Kc will also decrease. So know the relationship between your reactants and Kc and your products and Kc. Now remember, when they ask you what's going to happen to Kc, and they tell you that the temperature has changed, whether it has increased or decreased, you must work out which reaction is endothermic and which reaction is exothermic. Once you know that, you can work out using the formula what is going to happen to Kc. That's very important. Okay, so let's continue to 3.6. The initial reaction now takes place in the presence of a catalyst at 150 degrees Celsius, which is the original temperature. Describe the changes that will be observed on the graph between T0 and T60 seconds. So they want us to look at the first part. That's when the reaction comes to an equilibrium and when it reaches equilibrium. Now remember what a catalyst does. It creates the same amount of products, the same equilibrium is set up. The only thing is that the time that it's going to take place will be less. So try to imagine that the same graph is going to be taking place. However, it's almost as if you're going to squeeze the graph to the left, and what's going to happen is going to happen in a shorter time period. So this part of the graph is going to be more steeper. So you're going to go up like that, and it's going to flatten out a little bit sooner. The graph flattens out at about 40 seconds. So now it's going to flatten out about 30 or 20 seconds. So it's almost like the part of the graph is being squashed to the left. Okay. The gradients of all 3 curves will be steeper and reach the same equilibrium values, and you can say in a shorter time period, if you want to add that to your answer. Okay, that's the answer for 3.6. And you can also say the curves are more horizontal. So this curve will be more horizontal at same equilibrium value before 40 degrees reaches same equilibrium sooner, or you can say it will reach the same equilibrium in less time. It's a lot easier to imagine and focus that this part will be more steeper or more parallel to the y-axis. Okay, that's the answer for 3.6. Let's continue. Okay, now we've actually come to the end of part 3, and I would like to wish you all the best whenever you're going to apply this. And remember, success is not final. Failure is not fatal. It's a process. It is the courage to continue that counts. Have the courage to pick yourself up and to continue practicing exam questions. It will always count in your favor. Thank you. And I hope that these videos will help you and will strengthen you and give you a little bit of a better footing when you're going to answer exam questions. And that's all from me for chemical equilibrium. And I hope to upload new videos and to help you with the next topics in grade 12 chemistry. All of the best. Goodbye.